All right, so I'm assuming everyone can see my screen. So I'm still using the same notebook that we have used since our first session. All right. And yeah, the last thing that we discussed was the k-means algorithm. Remember? And we encountered a problem in the beginning. And if you guys remember, that was because of uh the way that the data was not normalized, right? Like the first chart that we managed to produce was not really what we expected, right? Like um we were supposed to separate them into three different clusters, but we only see like majority of them is it's one-sided to one cluster, right? Like it's not impossible, but it's very unlikely that it's gonna be like that. So it's very rare for something to be so one-sided like that. Um, so yeah, that's another thing that you always have to be careful of when you have data that are too far apart. All right. So there's bigger maximum and lower minimum. So you have to be careful of those ranges. If they're too far apart, you're gonna have to normalize the data first. And then after that, use that data as your new set of data, pass it to the algorithm, then it will give you a more accurate result. Okay, so that's normalization. Okay, and just a quick recap of what those graphs are. I don't know if you guys were able to reproduce this one on your end, but here you go. So I'm guessing this will run because I didn't run the first one, but let's give it a go. So we haven't been able to discuss much on the graphs, right? We were mainly just able to produce it. So we need to run this first. And after that, have the variables already. So now this can run again. And so warning, logical course, all right. Sub process, okay, that's all right. It's just because we did not declare how many threads we're gonna run. At this amount of data, it's not really gonna matter much, but when you're in the range of hundreds of thousands, maybe, then you might want to indicate properly how many threads. All right. So this is related to your processor, right? How many threads you want to use on your processor to run your program. All right. In this case, it's defaulting to whatever the default is. So I don't really change it that much. I don't usually tackle data that big. Um, because when you have data that big, usually you choose the data that you want, right? So it gets smaller and smaller. And then here comes processing data, remove all the blanks, the NAs, the irrelevant data, the data that is hard to distinguish, right? Like, do you remember the one that I showed you last week where there are certain values in our data that was they had mixed values. So there was in that one row it indicated that there were two types. So that kind of data should be um should either be removed first, place it somewhere else, and then you get back to it later, or you go ahead and fix it directly, right? It's good if it's just a few of them, but if there's a lot, then it's very time consuming. So If it's the data set's too big, you would do it programmatically, which would take a very, very long time. And it could get really, really complicated, which is not really the goal here of this course. The goal here is to teach you, get your foot on the door on where to start, right? And then from here, you can go on it on your own. Okay. Right. So supposed to run this. Let's scroll down. All right. So this is what a k-means look like on a scatter plot. So we're using a scatter plot for this. Okay. Now we have, as you can see, it's separated into three colors. I'm using the Virilis CMAP for this. The CMAP is the color mapping for how it appears on your screen. So there we have violet, yellow, and green. And also, I was able to get the data. Where is it? Yeah, this one. So the means, right? I was able to get the means of each category or column, right? And each row here is a representation of each cluster. So on the left here, it's 0, 1, and 2. So remember on the first one of the first step we did, the processing of data, is that we added another column, right? We added another column to indicate which row belongs to cluster 0, cluster 1, cluster 2, right? But that was determined by the algorithm. Okay. And now we have these data. So these two are what we really need, the graph and the cluster centers. Okay. So we're going to be discussing this one first before we proceed to the next algorithm. Okay. Now, understand that we don't really have a name for them yet because we're still at the part where um, we get to see the data visually. We got the means of the data. So now we're at the stage where we get insight. We, um, you know, try to understand what the data is trying to show us. So we know that we have three clusters because that's what we decided. That's what we want to classify the cars with. Okay, that's what, let's say, the management wanted. Okay, I want you to, let's say the order was, I want you to classify the cars into three types. All right, and then we'll based on that, we'll create a certain product or a certain promo, a deal, whatever. So um, now we have three clusters. So we'll start with cluster 0. We'll focus first with cluster 0. So let's see. Mm, we are trying to compare, right? Battery capacity versus horsepower, right? That's what we're trying to get here. And let's see. So we have lower horsepower mostly for these cars compared to cluster 1 and cluster 2, right? And then for the battery capacity, they are of a lower amount as well. So again, we're only comparing these two, right? But if we expand our view, total speed, right? It's lower. Here, performance, km per hour. So this is acceleration, how fast it can go from 0 to 100. So it takes roughly 10 seconds, right? So it's a bit slow, okay? Car prices, now that's a big difference from the cluster one and cluster two. So this is the average price of cluster one. Okay, it is an average of 4 seats, 4 to 5 seats, and a torque of 220. So uh, it's generally not that strong, right? Compared to engines, right? Okay, what else can we get from this data? Mhm. All right, so that's what we can read from cluster zero. I think that's it. The yellow one, cluster one, right? It's somewhere in the middle. So it has what? It features more horsepower, a higher battery capacity compared to the other two. Um, Total speed is also a bit high, a bit faster on the acceleration side, but we have to take note that the yellow ones exceeded and goes over the right side. Okay, so we can kind of see that as it goes from left to right, the battery capacity gets bigger and bigger, right? So odds are the vehicle also gets bigger and bigger. Um, the horsepower, right, as you go up, the engine also gets bigger. So as you can see, the trend is kind of like going upwards to the right. So the more you see the dots on the right, the bigger the machine is. So that's why we have um, some of it is kind of like clashing with the data with the green. Okay. But not all of it, right? Only some. So let's see. What else can we get here? All right. Now the data, the mean here is not really reflective of what the graph is, right? So based on the graph, you can kind of see that cluster two here has a higher capacity and a higher horsepower, right? They should be of a higher capacity and a higher horsepower because they belong somewhere from the middle up, right? Here, going here. So they should be bigger and they should be faster. But the data that we see here is not really corresponding properly. Let's see. Or cluster one. Now this is yellow is cluster one, cluster two is the green one. Mm. All right. So yeah, we can classify the data like this, right? So mm, the cars sort of like sort themselves out um, properly to a certain level, right? It's almost like uh, from here to here, these are the cars. From here to here, these are the cars that fall here to here, and some outliers at the bottom. Um, it's another cluster. So there's kind of like a natural grouping happening with the cars. Horsepower, on the other hand, rises quickly, as you can see, with engine size, but around 600 or 6,000, it starts to stabilize around here, right? So the graph sort of goes towards top to the right here, and then somewhere around here, it starts to like level down. Okay, so uh, it stabilizes around this area, except for these outliers. Okay. Mm, price, in terms of price, so we have only the data to see this one. Um, right. Well, we can generally say cluster one is the most expensive at this point. For the seats, let's see. We can see that cars with higher performance, as you can see here, 3 seconds higher horsepower, generally have lower seats. So two, three-seater cars. And then what else? I think that's all that we can take. Obviously, a higher torque corresponds to a higher performance, so this makes sense. Uh, so let's classify our data. We can then say that cluster zero will classify these cars as family cars. Or family cars or budget cars. Let's say we want to classify like that. And then cluster one with the highest performance, right? Highest horsepower, highest prices, we will classify them as the high-end cars, or in other words, the luxury cars. Okay. And then for number two, cluster two, cars that belong to cluster two, they have a larger capacity, a larger horsepower compared to cluster zero. So, but the price is not really that much expensive. So, we can probably say this is where the mid-level cars are. So let's say SUVs, right? Um, if we include heavy machinery, they would be in cluster one. So if we had some data in our data set that were, let's say, used for boom trucks, right? Those kind of that lifts heavy stuff. Obviously, it needs a higher capacity and a higher horsepower to lift heavy things, higher torque. So construction cars can also belong here in this criteria. All right. So that's it. You can present that kind of data to the ones that requested it. And based on that, they can kind of give some idea on how to proceed. Like, do we like prioritize first the luxury cars, or whatever their plan is for dividing the cars that they have? Let's say there's an inventory for cars, um, per category, per cluster, right? In this case, so we have three clusters. So set the family cars, we have the SUVs, and we have the high-end luxury cars. So we'll uh, maybe we can set that up depending on the site. How you showcase the cars on your site. So there's three sections. Then there are three different customers that you have. So depending on the customer, you can kind of lead them directly to what cars they might be interested in. And if they suit their needs, right? And if you introduce the car that suits their needs perfectly, then the odds of them buying the car might increase, right? And that's one of the trick, really. Just give the customer what they want. That is within their capabilities. So if you see that they're a family type, odds are they'll buy a family car, but they can probably go to cluster two, where the SUVs are, um, and sell that one to the customer, right? So yeah, that's pretty much it, what we can get. Then we can compare this one, right? The insight that we gain from this, the data, we can compare this one to the other algorithms that we'll get later and see if the result matches, okay? So if the result matches, then it just adds on to the credibility of your result, right? Like we've tried this on any algorithm, the results are always the same. The cars are divided into these things. Okay, if we divide it into three things, um, it's more effective, right? Like um, it's much more effective and a lot simpler for the consumer to identify, right? Which was our budget cars, family cars, and luxury cars. All right. That's pretty much it. Any questions with key needs? All right. So I'll take that as a no. Yeah, not so far. All right. Anyway, you can just review this one, guys. Anytime you want. The recording is available for everyone for life. So yeah, you can always review this one anytime. All right. We're done with K-means. So I'm just gonna leave that one there. I'm gonna go to the next one here. Okay. So the next time that we're gonna learn is something called hi hierarchical hierarchical cluster. All right. So again, this is a supervised learning. Um, let's see. So basically, what we're gonna use here for the graph is something that's called a dendrograph. So we're gonna use that one to show data or cars that are more similar to each other. And then you can put that on the graph, and then it will start to form clusters. All right. You'll see this in a minute. So based on that, right, we're gonna uh see and compare the results and our insights if it matches with what we have in our key. So since we divided it into three, we're also going to divide it into three clusters. Okay. All right. So yeah, the underlying theory, no, wait, the underlying, uh, how do I say this? The underlying concept for hierarchical clustering is something called the words method. So basically, it just combines or merge similar observations. That's basically uh, what this algorithm is trying to do, but it's more complicated underneath, right? What matters to us for now is that uh, it can help us, right, classify things by clustering them together. So that's what we're gonna do. So first, we're gonna have to refer to it. This one is under SciPy, the cluster dot hierarchy. import linkage and pentagram. Gonna use these two. Um, right. So we're gonna build first the linkage, and then mm, let's see. After building the linkage, mm, I think we can just declare directly that we're gonna use the words theory for this one. Yeah, the word method. So from that, I think that's good to go. So if we say linkage, we'll save it to the linkage matrix variable, and then we'll call linkage directly. So as you can see, I'm just importing it here because all the other things are loaded at the top, right? So I'm just going directly to the hierarchical clustering part. Um, we're gonna use, right, our normalized data. Our normalized data is saved in this variable, if you remember. So we are using the standard scalar, pass it here, and then from here, fit transform, fit it to x. X is yeah, fit x to the standard scalar, save it to x scale. So we're gonna be using x scaled at this point. Okay, this is our normalized data. And then all we have to do is declare ward, right? There are other methods available, but ward is the most common one and usually the simplest one to do in the beginning. All right. So the linkage here, the linkage function compares pairwise, right? The distance between all the cars. So it's computing it by distance, right? This is also one of the reasons why we had to convert, if you guys remember, we had to convert some data, some data into number equivalents, like the car names, the engines, and the company names, because if they were words, it can't use the hierarchical um, algorithm. Okay, so we need to represent those words into their numbers equivalent. Okay, sorry. Okay. Um, right. So it computes the distance between all the cars, and then it merges them. It merges the similar pairs step by step until everything ends up into one big cluster. So if you kind of visualize it that way, pair, pair, and then um, another pair at the top, which one's closer until it reaches to the very top. So it's gonna look like some kind of tree. Okay. Okay. Let's see. Mm, I think this is it really, if I remember correctly. We don't need anything else. We're already done processing the data. So all that's left is to pass it directly to the algorithm. Yeah. So we can go proceed directly with plotting it. Figure, big size. So this is just the size of our figure. Then the graph, linkage matrix. Then we pass in the labels that we will need. This is under cars, DF, company names. values. And then leaf rotation is equals to 90. POT, title, let's title this one. Let's do X label, car company. I don't know why it's not returning properly. DLT dot line label, distance, DLT dot show. All right. So just for context, if you guys want to search it later on, um, method word is the most common, but we also have single, we have complete, we have average, and then we have word. So those three can search this one and see the difference. Okay, it's never closed. View line numbers. Line 7 was never closed. Okay. Dendrogram, big size. Times. Oh, okay. This is a attribute. Uh, and all right. So it's processing. Let's give it a moment. Three colors. Right. So it's not really visible at the bottom, but we are using car company as one of the data that we're trying to like see if it can result into three different um clusters as well. Based on just color, they really are separate, right? So the lines that you see here at the bottom, okay, these are our car names. And then we just rotated them by 90 degrees here so that they all fit perfectly, okay, in a smaller area. But the challenge is it's not anymore readable, but it's there. Okay. The car names, each unique car name is there. Okay. The height, right, of a vertical line, like this one. Okay. So this represents how far apart, or in other words, how dissimilar they were before merging into one line or merging to the height of the y-axis distance. Dissimilar, dissimilarly, um, yeah. So the taller the merge, right, the less similar those clusters are. So the taller the merge, the less similar those clusters are, right? That's one thing to consider. What else can we have here? Let's see what else can we get. Hmm. Generally, we can just read this one as two clusters because technically there's just two colors. The one here at the top is just encompassing everything, all the cars entirely. So we're gonna have to do something else. So that would be broken down into three clusters. All right. Mm, all right. So another method for us to do this, is to actually cut a line somewhere in our graph. Okay. So not physically, of course, but an imaginary line. Like we're gonna cut somewhere around here. And if that happens, then instead of two colors, we're gonna see three because it's gonna hit these two at the bottom. And whenever it's hit, uh, it will create a new similarity between them. Okay, so a new vertical line. All right. Okay. Um, where do we continue with this? Okay, let's try this one. Let's put it in another cell so that we can compare. From sci-fi cluster, where to import F cluster. Okay. Clusters, matrix, T is equals to 5, criterion is equals to max clust. And then as this one to parse the F, and cars, good F, and two, hmm. We are just gonna count them. So we're gonna be using value counts. Okay, I think this is enough. Let's try printing it out. Figure image, matrix, labels, cars, underscore, yeah. But we're using company names, so we'll use company names here still. Um, what else do we need? We need the title or the AX line. AX and hmm, zero color is supposed to bracket it so that it matches what we're wearing. Table is cutoff line. right? So that's EX H1. Mm, yeah. So this is the one that's going to appear later on as a single line on our graph that will determine which part is being cut, right? And which one are we trying to measure, okay? Mm, Bible. And then finally, okay, these are actually friends. Uphill. Cluster two. Let's use cluster two. Mm. Six, six. Undetermined string. Line six. Nine, nine. Alright, guys, give me a moment. I'm trying to debug this one. Cutting line is not appearing. This was supposed to be divided into three categories. Why is it not working? Gonna take a look at the moment on their documentation. I might have forgotten a single line, or maybe several. Let me just check. All right. So I think I was actually looking at the wrong one. So it's down here. Parentheses. series it's all right. So, um, all these for the delay. Um, the one below here, we're using F cluster. All right. Um, so, so all right. So what we got here at the beginning, if you remember, is that um we just directly passed it to the algorithm and then created a figure, right? But we wanted three, right? We wanted to separate three categories and see if we can actually get the same kind of result with k-means, right? So in this part here, we're going to be using F cluster. And to actually decide how many clusters we want, we can cut, right, this dendrogram horizontally at a certain height. So that height will be our distance, okay? So if you, so a rule of thumb when you're trying to cut a dendrogram is that it cuts through the fewest vertical lines possible, okay? But still separates it into distinct groups. Okay. So if you want a distance of 20, it will cross two, three, four major branches. So it will create around 3 to 4 clusters. If we draw it around 30, um, let's see, or 40, you'll get fewer clusters. So that means bigger groups. If you draw it around 10, you'll get more clusters. So that means you get to classify your cars into more diverse types. Okay. That's what we're trying to say. But what we're trying to focus is we're trying to get three as well. Three. Okay. So if we put it around 30, distance of 30, we can get there. Um, we can get there 3 to 4 clusters. So that's our target. Okay. So let's see. Mm, 1, 2, 3, 4, 5. Hmm. If we use 20, so The dendrogram here that we're trying to do, we're trying to use the color threshold attribute or property. And all the others still remains the same, as you can see. Labels, leaf rotation. The only difference between that and this one is um, we're trying to use the color threshold to separate the colors into three types, right? And the F cluster here at the top is for uh let's see, cluster two. We use the number 25 here to give us that. 1, 2, 3, 4, 5, 6, 14. So 14. So I guess this is good. Color threshold of 35 would give us roughly 3 to 4 clusters. And you can see that with 4 different colors. Okay, so the orange, green, the red, and the overall one, which is the blue color. Okay. Cluster two here, we need to get that one out. So where did this go? And we get that. So there we go. The F cluster that we used here, will group the data into four, right? And we're using the linkage matrix from what we got here at the top, right? We're still using the linkage matrix here. And then, so it's pairing up all the similar cars, right? And it clusters them up here. The T here will indicate how many clusters we're gonna group them up. And then the criteria will be the max cluster. So this is usually the setup for F cluster. And we're gonna have to match, right? What this will print out. Okay, it has 4 clusters. And with our graph, which is also showing 4 clusters. Now, their data should match, right? This is why I was confused earlier, because it wasn't matching. So right now we're cutting the graph to a certain section so that it's divided into 4 different categories, 4 different clusters. And cluster two, on the other hand, here we're naming cluster two. is also divided into four different clusters. And we can see that reflected here on our data. So cluster four, there's only 10. So this must be the red one. Cluster one, it's 132, 162. All right, so it's not matching again. Let me adjust this one. This data should match with what we have here, since uh it's using the same data set. Let's see. A91 cars. No. If I use third port, that certain is not the one. So 30 is how many clusters? One, two, three, four, five. And if we group this one to five as well, let's not force it to three because it's rather difficult. Let's try five since it seems the most easiest. Five as well. One, two, seven. Hmm. It should divide this one further into two more colors in order for this to match, I think. But it's not dividing into two colors. Why? I am missing something here that will make this correct. Hmm. Because all this is showing us how many cars there are per cluster, right? It's showing us how many cars there are per cluster. So right now it's not really matching because the green one is too big. So I think we should divide the green one more time in order for this to work. So in order for us to divide it further, we need to put down straight 20 and 5. So there's a lot of trial and error with this. All right. One, two, three, four, five. And then the last one is the overall. Okay. All right. Okay. I think this makes much more sense now. So now we have, let's see. So cluster five must be the fewest one. So it's here. Cluster two is 96, must be the green. Cluster 3 is 295. It's the red one. Cluster 4 is 162. This one, the violet one. And okay, I'm gonna go over that again, but in reverse. Cluster 3, 295, the biggest one is the red one. Cluster 4 is the violet one. Cluster 1 is the orange one. Cluster 2 is the green. And cluster 5 is the brown one here at the very end. All right, so this is the setup that we need to do. You need to set your color threshold to 20 and then set your F cluster to t equals to 5. So it will divide into cluster your data, leakage matrix, and count how many cars there are. And it should reflect properly also those numbers here as well. Okay. So unfortunately, we can't match it properly with k-means with three clusters, right? It was very difficult to match it. That's why I was confused earlier. The numbers were not matching up, and we had to do some troubleshooting on it, just to get it like this. Um, for presentation purposes, we can put a line somewhere here. We can add a line so that the audience will understand more where your threshold is, this one, because they can't see the code, right? So you can describe to your audience that you're saying we're gonna cut it off over in this line in our graph. So how do you do that? There's a function for that in matplotlib. All you have to do is add a horizontal. So plt.ash line y is equals to how high you want it. So it's 20, right? You can set the color to something that's very visible, like black. Line style can be dash dash maybe. And then label will be uh cut line, something like that. Yeah, no need to indicate the distance. It should be visible. That's it. Okay, so the one below is a lot better than the one above. You can't really do anything. There's just too many cars for this to divide it into two. Um, it's somewhat lacking. I mean, you can present this one as this, but it's not really helpful to anyone. But this, right? It's more subdivided into different things. So, in our K means we divided it into budget cars. We have um the middle class type, the SUVs, okay, and then the luxury cars, right? So let's see what else can we get here. So a bit of a comparison between the two. In K-means, you have to, if you remember, you have to declare first um, at the beginning how many clusters you want, right? But in the hierarchical clustering, you can actually get the graph directly without any clustering yet. And you can decide for yourself how you want to cluster them out, right? So you can kind of see that one here if you versus that one with the k-means earlier, right? Um, the next one would be mm, for the visualization purposes. So I think in terms of visualization, right, it's better to represent the data like this. Um, it's a lot easier to divide them this way compared to k-means. And yeah. Mm. However, if there's one thing that's a problem with this, um, because we're using linkage, it has to pair up similar cars, right? But with that process, pairing up, right? Whenever something like that is involved, it consumes a lot of memory. It consumes a lot of processing power. So right now, we don't really feel that effect because the data is not really that big. But um, it gets more complicated when you're dealing with bigger data sets. So that is the time when k-means actually shine better because k-means is a lot faster. The algorithm for k-means is a lot faster compared to hierarchical clustering. Although the underlying reason for that is out of my abilities really to discuss. It's a lot deeper maths, really. So this is where we usually play around as data scientists. We just use the algorithms that's available, and then we're more on gaining insights and using the correct data and presenting the output to our audience. So just with that alone, we can do a lot with our research because as you know, there's a lot of data going on nowadays. We can get it from anywhere, especially in phones, right? Where do people tap? How long they are watching? Um, what ads were clicked, right? So yeah, everything is tracked nowadays. Um, let's see. All right, so another key takeaway for a dendrogram, you can kind of remember that this algorithm is basing it on the distance. Um, we converted the names into numbers, right? We're basing this on car company names. We converted their name into numbers, right? And based on some mathematics, it gets some kind of distance between different names. All right. And this is what the vertical line is for, how far apart they are, how dissimilar these two things are before they merged into one at this point. That's what we're trying to say. Now, with that, you can kind of see that there's a lot of cars here at this distance. They are all similar, right? But the further and further we go up, they start clumping up together into clusters. That's what we're trying to show. That's what we're trying to understand, right? Like these are the cars that are clumping up together. So we can see that there are more cars that are belonging to cluster three. So we can reserve those cars as maybe this can affect pricing a little bit. Since there are more cars in cluster three, we can price them a little bit lower compared to cars that are at uh, cluster 5, right? And we can price them a little bit higher. That's because they are a bit few. So odds are these are the luxury cars. If you were to look deep into it, these are probably the luxury cars that we saw before. Okay. Um, what else can we get here? 104, 100, and 162. So we can roughly say these are the ones in the middle, right? Middle end. So these must be where the SUVs belong, cluster 1 and cluster 4. So these are the cars that um, give us good performance and also good pricing. So it categorizes them here. And cluster 5 too. Okay. So if they are not luxury cars like this one, they must be unique. So the engine types that are unique. So they must belong here as well. Because if they are not unique, then they should have belonged to cluster 3, 4, or 1. But since they are here, their engines must be unique. Especially so for number 5. So they can be considered as outliers as well. It's really right there at the end, right? Mm, mm, yeah, I think that's all I can get from this. You can decide how you want to interpret or name the different clusters. So yeah, let's say 5 is the luxury one. Let's say 3 is the budget. 4 are the SUVs. Oh no, wait, yeah. 3 is the budget. 4 is the SUVs. 1 is the lower to mid. All right, if there's something like that in between. And then 96 are the unique cars where there's not really a lot similar to that. I can't really think of anything cars. Mm, unique engines. What are unique engines? Maybe hybrids. These must be the hybrids, the ones that run on electricity and also runs on fuel. So these must be the hybrid ones as well. Yeah, I think we can name them like that. Okay, so that's it for hierarchical clustering. If you have any questions, let me know. If not, then we can proceed to the next one, which is called PCA. I go here, PCA. All right. So PCA, let's see. Mm, the description that the documentation gives us is that it Uh, simplifies, this is what it gives us, simplifies your data set into two main dimensions, so X and Y, that capture most variance. All right. And PCA actually means principal component analysis. Okay. And Yeah, that's what PCA means. Let's see. So what does this mean, right? What does simplifying your data set into two dimensions, two main dimensions that capture the most, the variance. So what is variance anyway? So variance is like, um, how do you describe variance? Variance is like, what's an example? What's a good example of variance? Basically, it's how far apart, yeah, right, their um numbers are, their mean, basically, how far apart they are. So the greater the variance, the farther apart those things are. The smaller the variance, the closer they are. Okay. So a high variance means that the data is actually more spread out if you say high variance. While if you say something that has a low variance, it means that it's clustered towards the mean, right? So that's how it's trying to group our data to different clusters. Okay, so by using variance, right? Um, what else? So PCA. Mhm. Um, basically, let's go back to our data. I think it's better to see what our data is. See age of the 71. Decision tree, unsupervised data set. All right. So let's say it's gonna choose, um, it's gonna choose something like the horsepower, the torque, right? The battery. Okay. So it's gonna group our data into two, right? Combines them to smaller numbers. And after combining them into smaller numbers, it's basically reducing our entire data set into two dimensions, right? Like what I said earlier. It's reducing it into two main dimensions. So everything, all the columns that we have, it's gonna compress that one into one, two dimension, right? And then we're gonna create a graph out of it. That's basically what PCA is gonna do. Okay. All right. Mm. So we're gonna create two what data set are we gonna use? We're gonna use what what did we use here? We use X scale, right? Mm. All right, let's pass in our normalized data for PCA as well. It doesn't make sense if we will use our original data since it will also affect, yeah, it will also affect our result. So yeah, we're still gonna be using our normalized data. From scalar composition, import PCA. We're gonna call PCA, save it to PCA. And component properties and components. Components, I think with an S. The two. Mm. So why two? Again, two is the easiest because it will reduce all your columns into two dimensions. Okay, you can go above, right? So it's gonna choose. So the first group will be the one with the most variance, right, in your data. The next one it will capture is the one with the next most variance, but it's uncorrelated to the first one, right? That's how it works. Um, yeah. So PCA underscore result. You access PCA now, and then you fit the data, fit transform. So I'm sure you've noticed that the commands are fairly similar, right? Transform, X underscore scale. Then we plot it now, PLT figure. So hopefully this time we won't be troubleshooting a lot. Big size, 86. We have two dimensions, and usually if there's two dimensions, the best time one that we can use is a scatter plot. So we'll use a scatter here, PCA underscore result. Um, we're gonna start from the beginning and then up 0, PCA result will start, and this first column, column one. Oh, I mean the second column, yeah. Um, C course, yeah, this is the column that we will choose. In our X scaled, we have the cluster column. We're going to use the cluster column to use the proper capitalization. And then CMAP, I'll still use the greatest. All right. PLT, the title. This will be PCA. PLT, the next label. This will be PC1. PLT, the Y label. Y. Y label PC2. And then PLT that show. This should be good. All right. Okay. So now we can relate a lot easier with this to k-means versus the hierarchical uh method earlier, right? So as you can see, PC1 and PC2, right? Even k-means we only consider what battery and the horsepower, right? We were only looking at two features. PCA here takes everything into consideration and then compares them together and see where it leads us. So now it's still giving us around three clusters, right? And yeah, so we have even after we said that divide it into primary components, which is what usually is the setting for PCA. What is happening? Okay, there you go. We can still see that it's separated into three clusters. So we did not um explicitly indicate that we separated it into three clusters. This is what the algorithm resulted in. Okay, so we can clearly see directly that the result here coincides with what we had with k-means, right? So it makes a lot more sense now. It gives us, more confidence that our insights maybe, right, be correct, and then we can safely give this out as our output. Okay. Um, so we can see here that PC1 ranges from -5 to 12.5, and then from -2 to 4. All right. So these are the measures of their variance. Okay. Now, as you can see, the ones in the middle here, right, they are grouped into clusters, and then starting from around 1 until -5, it's grouped into something else, and then -1, and then from 1 up to 12.5, it's grouped into something else as well. So there are a few outliers as well here. So this part, it coincides with our data with the hierarchical clustering that we had some where's it? Where's it? Where's the graph? That's the one, this one. That there are some outliers in our data set. So we can only see that if we divide it into five, like this one, you can see it at the very end. But in our k-means, where's our k-means? K-means, uh, here, we can also see that somewhere around here. So our outliers are kind of really distinguishing themselves, right? So we can have some outliers here. This is comparing battery capacity and horsepower. Of course, you can choose something else. The result will be different, but odds are it will still be separated into three. Um, oh yeah, it will be separated into three because that's what we set the k-means for. This is what makes PCA great because um with a lot of features, right? We have a lot of dimensions basically if we were to graph that one, but it sort of simplifies these things by using variance, and it gives us this beautiful graph here. Okay. If you want to see what the algorithm was using, right, for PC1 and PC2, we can actually get that one. Let's see. Uh, let's, hold on. Let me go to the documentation first. So it's under components, and we have to use pandas. So we can say something like components of PCA. Let's say this will be under components. We access Panda, we use data frame. We passed in PCA dot components. It's under components. Columns will be x dot columns. Mm, what else is it? Yeah, it's using. So index here is for the names. So we'll name them PC2. GC1 and then GC2. Uh, Incomplete input. I forgot this one. The star attribute performance. Components. Oh, okay. It has, since this is a property, it's using an underscore. Hmm. So be careful on this one. The ones that create libraries, they usually add an underscore at the beginning or in the end. And sometimes it's not so easy to see because of the colors. But the usual meaning of that is it's a property that you can read. That means it's just data there. It's not a method or something. It's just an indication that what you're seeing is a data. Mm, let's say components. Why is it that? Oh, okay. I forgot to print. There you go. All right. So these are, this is PC1 and this is PC2. All right. Um, let's see. So right off the bat, I can see that total speed and performance are contradicting with each other. Okay. The variance here is negative on PC1. The total speed here is negative for PC2. So they're kind of opposites here. Um, let's see. Higher horsepower. So this has a higher value. So cars with uh, higher horsepowers will end up here in PC1. And then cars with larger batteries will end up in PC2. Okay. All right. So this is, hmm, by the way, these numbers, I don't want you to think of them as they belong to PC2 only or PC1. Since we're dealing with variance, it's better if you think of them as uh, weight. How how much does it weigh, right, for PC2 versus PC1? So for battery capacity, right? Um, let's see. By the way, for PC1, let's see. Let's look for a strong positive. So total speed is a strong positive. Um, Performance is a strong negative. Can see it as a strong negative. Um, so speed and performance, right? Um, Basically, we can say that um, no, they're opposite. Let's choose something that's within line. Speed, horsepower, and torque. So these are almost the same, right? For PC1, these are the highest values. For PC2, the highest values are battery capacity, car seats, and performance. The lower the better, right? For performance. Because the lower the number means that the cars that are very fast belong here. So we can kind of say that PC1 weighs more on the horsepower, speed, and torque side. So if your car has those things, you're leaning more towards the PC1. If your car has um, the capacity, right, the better performant ones with more seats. Okay, let's not use the seats. Maybe just the performance and capacity, because this makes more sense. So this is um, mm, it represents more power, but I guess maybe better efficiency, bigger, bigger battery, but higher performance. Okay, we can say it like that. So it's leaning more towards basically if your car has uh, bigger batteries and higher performance. So it will lean towards PC2. Okay. Mm, right. So we can interpret this one in a different way as well. So since PC1 is leaning towards horsepower and total speed, um, and PC2 is leaning more on capacity and performance, right? Um, we can interpret it like that. So PC1 will be for speed and horsepower versus this one, uh, capacity and performance. So that's what we're trying to compare. If you were to rename them, I would rename it like that. So horsepower and total speed versus battery capacity and acceleration. Okay. So that means, um, let's see. That means if this is horsepower and total speed, if we go to the right, it will have more horsepower, a higher total speed, but a lower acceleration. But if we go up, that means our battery capacity and also our acceleration goes up. So these things here, right? These are the luxury cars. Okay. And since it's going in that direction, right? So it's the green ones are going to the right of PC1, which is also meaning better horsepower and better total speed. And then as it goes up, it's also getting better battery capacity and better uh, acceleration. So these should belong to cars that are more performant because it's over on the right side. The ones on the left, right, indicates what? Slower engines, but it's also there's also a lot of machines, or there's also a lot of cars that are jumbled in here. See, there's a very high density of dots here, somewhere around zero. So I would say these have like uh what's this battery capacity, right? So it's going up. That means uh not really somewhere in the middle, but since at it's at zero, it's like at the minimum at that point. It's almost at the minimum, right? So we can say that these cars are at the budget point. So these are probably what we can say the same with the K-means, the budget cars, because they belong here, almost at the zero point, and they are before the zero point of PC1. So lower horsepower, lower engine power. Um, the top speed isn't that big. Acceleration should go down as well since it's going to the left. So these are probably where the budget cars belong, similar to what we got with the K-means. Yeah, they are kind of jumbled up here. There's a high density of dots around the zero point mark here on PC2. And lastly, the yellow one, we can see that it's mostly at zero on PC1. So that means it's about middle or average for horsepower and total speed, which is exactly where um, our mid-level cars stand. So the SUVs, uh, the hatchbacks, I think belongs to the budget one. What other car types are there? Sedans, so they must belong here in yellow, the yellow one. Yeah, so that's it. That's how you read this data. After naming it PC1, PC2, you can rename that one later on to something else. Uh, like what I suggested, horsepower and total speed versus battery capacity and acceleration. So yeah, the trend is that as you go top right, the the more expensive and the more performant your car is. As you go bottom left, um, it's not to say that it's inefficient, but it's a lot cheaper, but less performant. So some part of the yellow here is also have a high density around this area, right? So there's a lot of cars that belong here. Okay. Um, okay, what else? What else can we get from PCA? Um, what else can we get here? We can, let's see. There's another one here that they indicate. We can also get the variance ratio. So according here, this will show us the percentage of cars that belong to PC1 and PC2. So if we print this out, let's say this is variance ratio, and then it's under explain variance ratio. So there's a lot of things you can get by just by reading the documentation. It's just a matter of finding and navigating your way around it. Okay, so let's run this one. So it says variance. Okay, so it says here that the variance ratio will signify, right? So this is PC1. Um, 63% of the cars belong to PC1, and 15% of the cars belong to uh, PC2, right? If you add them together, that's zero point 0.3 and 15. That would be 73, 78. That would be 78, right? 0.78. That would mean 78%. So that means 78% here means, so it means that if you're over 50%, that means over 50% of your data is visible here. Okay, that's what it's trying to say. So that is a good indicator. Over 50% is a good indicator of your result. So that means this is a good output for us. Okay. Mm. Something else that I can get here other than that. But yeah. All right. Any questions so far? So it's getting kind of complicated, right? So even for me, I kind of got lost sometimes, so I have to refer to the documentation on how to get some things. I don't have everything in my head, but some of them I can somewhat remember how to access them, but not all. All right. The PLTs usually just repeat in that manner. So if you use it a lot, you can kind of remember some things and, just go along with it. Again, this is actually a lot easier if you were using something like Visual Studio Code, because as long as you can remember some part of it, like for example, earlier I had a lot of misspellings, right? And I can sort of remember part of the name of the property, but not all of it. So usually it will suggest to you the things that are it filters down in VS Code the things that you can use that are similar to what you're typing. So if I see RES, it will display everything that has an RES in it, all the properties that has an RES in it. So it's a lot easier, a lot faster, and it's easier to remember that way. So if I see PCA result and I say, oh, okay, this is the one that I used before. So there's actually no need for me to remember everything. I just need to remember that I use it once, and this was the property that I use, and I can somewhat wiggle around. Okay, just in VS Code without actually going to the documentation. And when I am completely lost, that is when I go back to the documentation. All right, so that's why I had a lot of misspellings whenever I'm typing out code. Just because we are here in Jupyter Notebook. Uh, but yeah, that's it. So overall, so far, it's been a good result, right? We have some good results. Some of them are, or most of them are coinciding with each other, right? Um, okay, what else? Mhm. All right. Since it's already 3:30, it's almost 3:30. I think it's time for a break. Anyway, we're only one more algorithm left, and that is the isolation forest. So that's the last one that we're gonna discuss. If we still have time, we'll demonstrate accessing APIs. Maybe we can skip the whole process of the web scraping part and go directly to how to access APIs so that you guys can explore more. Uh, yeah, sadly, I was not able to get some databases that we can use for free. I mean, there are some, but you have to pay them. But databases that are free. I didn't really find any, but you know, it's basically the same logic as what we were doing here. You're gonna use a library, and then that library will be the one that will connect to the database with your credentials. You're gonna input your credentials somewhere in your code, and then it's gonna log in for you and then access the data. That's basically it. That's how you access data from servers. Uh, yeah, but more on that later. Okay, I think we all deserve a break. Process the information that you have learned and then internalize for a moment, absorb, and maybe you can, um, you know, grab some coffee, snacks, get some energy back. All right. I'll see you guys here at around 3:45. Yep, I think it's enough. 3:45 or 3:50. Okay. So have a good one, guys. I'll see you later. All right. So I hope you guys had a good break. Let's see. Can I get a thumbs up if you guys are here? I think there's a lot fewer of us right now compared to earlier, but that's okay. All right. Thank you for the confirmation. Hey, James. Right. Thank you guys. Okay, let's go now to the last the last unsupervised learning algorithm that we need to learn. And this is actually called isolation. All right. Now, from the name itself, right, you can kind of guess what this is for. So this algorithm is actually used for looking looking for the outliers. Right? It's somewhat different compared to the other ones, right? This one specifically looks for the outliers in our data set, right? So, right, so okay. Now where was I? Ah, yes. It looks for the outliers in our data set or the data that behaves unusually, not like the others. Okay. The way that this works is that just like with random forest, right, and a decision tree, it's kind of the same thing, but what it does is it builds many random decision trees. That's what it's trying to do. Um, so it's trying to split the data again and again. And the weird data points that it will create get separated faster because they stand out, right? That hence outliers, isolation. Um, so each tree splits the data randomly, right? They're trying to split them up. Um, the normal points of the data take more time to split. You need to split more times to be classified as normal points. But the anomalies are usually discovered because they tend to come out in just a few splits. All right. And depending on how many splits it took to get to that point where we can see the outlier, it will create a certain score for that. And that's what the algorithm will do. It will calculate a certain score for us, and then that is what will give us a return. And then we can base our insights and conclusions on that output. So that's basically what it's trying to do. Okay. Um, yeah, so let's go ahead. This one comes from SK Learn and Symbol. If you remember, this is also where random forest came from. The Symbol input isolation forest. All right. And then you need to train the isolation forest, right? At first we need to have some assumptions. So uh the default thing is to assume that your data has, how do I say this? 10% of your data is anomalies. So it's just a ballpark number, right? You can guess whatever you want. It depends on this, how much, like, it's like the tolerance of what you consider to be an outlier. right? Usually 10% is the number, the magic number. All right. So you say, let's save it to the variable ISO forest, and then we call in the function. Okay. We call that property contamination. These are what you assume to be outliers. So we say 10%, so that's 0.1, right? Random state, we'll set it to 42, and that's it for isolation. Next is we create a new column, cars underscore df. No. And then you call the ISO forest, and then you fit the data, hit predict, and then the data that we're going to use is the normalized data. So X scaled, right? So pretty much in all our algorithms, we've been using the normalized data, right? So it just gives us more accurate output than compared to the normal, right? Next is we need to get the anomalies. So we save them into a variable anomalies. This is cars underscore f. Um, so the way that this works is that fit predict will give us one. This method will give us one for normal data, -1 for outliers. So that means we have to collect those that are -1. So cars df, cars underscore df again, but we're only going to select anomaly, but only for the ones that are -1. All right. Then you get print this one out. Let's say anomalies. Um, let's see. We can show the company names. Company names. We need to be exact with this. Cars names with an S, right? Next is cars prices. Next is horsepower with horsepower is capital P. Yeah, horsepower. And then last is total speed with the space. All right. So we can use these things. And then again, incomplete out anomalies. Okay, I'm missing the parentheses. There we go. All right. So these are the anomalies that we have. So there are 70 rows. We have 70 rows of data that is considered an anomaly. All right. Again, we are considering 10% of our data set to be anomalies. So it's basing it off of that one. Is there a correct way of choosing this one? Just like the k-means, right? K-means is it's really up to you how many clusters you want, right? It's arbitrary to you, the one that's doing the research. But there are scientific ways and methods to, get the most ideal one, but in the end, it's up to you as the data scientist, right? So here, I'm just assuming 1% is anomaly. It's an anomaly. And this is what we have. All right. So this means that there are over 70 cars that are potential outliers, cars that have a strange combination of values, right? So what is strange? Like maybe we can say too expensive for their performance, too powerful for that typical model, too slow for the horsepower. So that's very weird, right? Um, or if there are any rows with errors, that will also come out, right? Like if there was a car that's priced 5 billion, that would come up here. Okay. So yeah, these are what came out. Let's see one of them. So there's one. 5 million. This has a horsepower of 1600. So this is a potential outlier. Yes, it's too big. Um, all the others are within the tolerance of 10%. So that's why they're still included. If we were to be very strict with this, let's say 5%, some of these will disappear. Like the 300, 400s will probably um, disappear. Okay. But this is just a table, right? If we plug each one into a graph, right, we'll see something else. So let's try this one. Right. So let's say um, PLT dots gather parse underscore F parse rises mm, cars prices and horsepower. Yeah. So using these three features for now, you can choose the feature that you want, but for now I'm using this one. Cars DF. Again, as a data scientist, we are not really limited to one or two features, right? We explore every other angle that we can and see if there's a trend there. Or we start off from a general trend and then choose the specific columns or features that we need to look for that specific trend, if it's true or not. Like, um, what did we have before? The example that we have, like, is the um not the years of education you have correlates to a higher income, right? Something like that. So is there a trend that supports that one? And of course, we're gonna look for specific features that influence that, like the number of years, right? That's of course one of those features, or maybe the type of course, the uh how much it costs, right? The availability of the course in a certain region. So those kinds of things, right? Let's try using a different CMAP. I'll try using cool warm. Um, so cool warm, this will probably be red and blue. Um, yeah, so PLT dot X label, bars, right? PLT dot Y label, uh, course, power, PLT dot idle, isolation, whereas outlier, and then PLT dot show. It should be enough. All right. Um, all right. So this is mm, okay. Hmm. Trying to make sense of our output here. X scale. If we were to try and show something else, let's see. Mm, we'll try to put a label here. Label is equals to All right, I think the first one makes much more sense than this one. We can just remove this one here for now, so that we won't get confused. All right, I think this makes much more sense, but it's a bit counterintuitive, right? We set it up so that it will show us -1 as the anomalies, but clearly it's not going correctly, right? I don't think we did anything wrong. But it's showing up here. The anomalies are showing up at the bottom, right? Um, so how do we read this, right? Because obviously the outliers are these things, right? Because they are the one that's most separate from the group. Uh, like for this example, this is an outlier. It's too expensive. Greater than 1.45 exponent to the power of 7. And it's about 1,500 horsepower. So these are the luxury cars. Uh, for sure, these are luxury cars. So we know for a fact that these should be the outliers and not these things. So why were these flagged as outliers by the internal logic of our algorithm? All right. So, mm, all right. Let's try lowering the contamination and see if it changes. Because I think it's because we are setting it too high. Maybe 10% is too high. Maybe one is 20%, um, 0.5, 0.5. So bring it down. It's even more. Let's try a figure 30%. Hmm. It's getting fewer and fewer, but that's the expected response. 50%. It's still going here. It's not really recognizing these things. But if we were to say compare horsepower and car prices, right? Majority of the cars are here in this part of our graph, right? So each dot is a car, and they are heavily dense in this area. Now, one of the weaknesses of isolation forests is that it actually struggles with high density clusters. So we can consider this one as high density clusters. So this is actually one of those things that we call false positives. So it's reading this one as an outlier, but it's actually not. Where in fact, this is the actual outlier. So don't just take data for the output as is, right? You have to read between the lines and analyze it carefully if it makes sense. So it makes much more sense if these things were the outliers here and not these things here. Um, so I'm not really sure what we need to edit here to make it that that's too much. Wait, it's too much. Let's try 0.7. No, 6. No, combination. I think 0.5 is the highest we can go. So we can't go up with it. Um, yeah. So the graph still remains the same, only the red ones will differ, right? The number of red ones, because that's basically what the contamination was for, right? It's our anticipation of how many are outliers, right? But it failed to detect the correct data, which is this one. But we can still confirm it visually with our eyes from this graph. Okay. So yeah, it's still useful in a way. It's just giving us the wrong output, right? And that's really it. There's nothing much we can take from this aside from that. It's really just us figuring out which ones are outliers in our data set. So that's pretty much what this is used for. Anything else we can't really use this for. So that's basically it. All right. Okay, we're done with the unsupervised learning method. So those were k-means, hierarchical clustering. We also have PCA and then isolation forest. So each one has their own uses. But the thing that goes well together is you use PCA first, I think is the best because it kind of transforms your 3D data because you have a lot of dimensions, a lot of columns, features, and then transforms it into a very neat 2D graph, which is very easy to absorb and very easy on the eyes for the audience to understand. And then you support that with k-means or maybe hierarchical clustering to see that we can further classify these things into um, in terms of more specific features like horsepower versus price or speed, battery versus acceleration. So those kinds of things, right? Depending on how you want to present your findings. It's usually a combination of those things. So yeah, so that's it. I hope this has been very educational for you guys. I know there were some setbacks, some parts where I was troubleshooting, but we still made it in the end. So that's nice. Um, okay. So the last thing that we're gonna do, um, I think there's only enough time for me to demonstrate accessing a API using Python. All right. So one of the sites that I like to demonstrate this one is this. It's very easy to do. Codes to scrape. All right. Um, I'll add this one. Uh, wait. I think it's this one. Yeah, I think this is it. Okay. All right. So this is exactly like how Facebook works, how TikTok works, how YouTube works. So yeah, you ever see the thing that there's data content already loaded on a page, but if you scroll down, right, you're gonna see some blank, but in a few seconds or maybe even less than a second, depending on your data, it's gonna load up something new, right? More data, but you can see that it didn't really uh change. So this is for the scroll, but the one that I'm looking for is something else. Mm. Spatialization, default to JavaScript. States. It's not listed here. It should be under API. Um, hmm. All right, so I think we'll just use the scroll one. All right. Okay, so what's really happening with this behind the scenes? So behind the scenes, what's happening is that when you scroll down and you reach a certain point, like this one, the browser, right, whatever browser you're using, is actually making a request to the server. Now, we can't really see that happening, right? They often hide that one because it's uh, not really helpful to the um, regular person, right? But if we go to the developer tools and go under networks, right? If we just reload the page here, okay. What you're looking for is a specific request. It's, hmm, let's click one. Code still, okay, page one. All right. So page one and page two is requesting page one and page two. And it is being displayed here right now. So what we are looking here is two pages loaded on our site. If I were to scroll down in the network tab here, you should be able to see another thing like this that will request for um another page, right? So let's see. We go scroll down. All right. So as you can see, two more things pop up, page three and page four. All right. Um, yeah, so all the data that you need for your request is stored in this single file. So you have your headers here. Uh, yeah, so if you have some keys or some authentications, it's gonna be in here as well. But yeah, so that's how it does these things, right? So what can we do? Well, we can use this one, right? This specific request. So all we need is actually this one, the request URL. So if I type this one and then get equal one, right, or equal two, it should show us or it should give us a response, right? So here's our payload. This is our request page one. If the response from the server is here. And as you can see, the response from the server is in this format, right? This is what we call a JSON format. This is how data is usually transferred between different computers over the internet. Okay, so JSON is just one of those methods of transferring data. There's a lot more, All right. But JSON is the most basic and it's the most used format in the internet. Okay. So learning this one will be very beneficial to you in the future. All right. Okay. So um, don't um, don't concern yourself for now with how it looks, right? What you need to concern yourself with is the way that it looks. Wait, oh, wait, that's wrong. What you should be concerned is the content right now. Okay, so let's compare it. Page one, the first one is about Albert Einstein. So we can see here we have a quotes list, right? But this is JavaScript, so it's not called a list, it's called an array. But technically, they are the same thing. Um, let's see, Albert Einstein, yep. And here's the code text. The world as we have created is blah, blah, blah. So this one here, from this to this is one code. And then this to this is another code of a different author. Now, what I'm trying to prove is that this is all you need, right, to access the data. This is the API. This is your application programming interface. This is what you send to the server along with all the other defaults here to request for the codes. All right. Now, as proof of that, if I were just to copy this one and then paste it somewhere here, page one, for example, it will give me the same thing. It's the same JSON object that we saw here. In fact, if I were to pretty print this one, it has the same format. See? So the pretty print here is just something new in Chrome that you can do. So anytime that you are viewing a JSON object, if you click on a check mark, it will, um, how do what do I call this? It will indent it automatically for you so that it's easier to read for each nesting that is happening. Um, so again, it's the same thing, right? The world as we have created, blah, blah, blah. It's Albert Einstein in the beginning. So we know that what we see here is also what we get here, right? Now, what do we need to do? So basically, all we have to do is request the same API, but just change the page number at the end. If I were to say page four, I think you can kind of guess where I'm going with this, right? So now, this is an API. This is what we call an API, right? So um, this API is in the form of a URL, and you use this one to access data from the server without actually going to the website. That's the point, right? This website is just accessing data from the server and presenting it in this format. It's a lot more readable compared to this one. But technically, we can just use this, get the data, and then do what we want. Do what we want with it, right? So let's do that here. Okay. So we start with importing requests. Next is we'll import pandas as well. We're gonna get the base URL. So that would be this one. No, that's not the one. This one. This is the base URL without the last slash. Okay. The API end is what? Base plus API slash codes, right? Because this is what's the end at this point, API codes, and then question mark page four, right? But it's okay if we're only up to here. We can add that last part later on because we're gonna create a loop that will access each page over and over again. Okay? No, not each page, each succeeding page. We're gonna do it programmatically. So we're gonna start obviously at page one. We're gonna set page equals to one. And then we're gonna create a loop, right? So we're gonna say while true, Okay. Let's see. Well, true. mm, Response is equals to request get API params or the parameters that you want. And this property here will automatically add the last bit, which is the question mark page and then the number. So we say params and then page, page. All right. This is equal to page. As you can see, it's formatted in as an object. This parameter is formatted as an object. Okay. Now, take note for other APIs, there might be other parameters. So every time you see something like this, and with an equal sign afterwards, that is considered a parameter. And then you can declare that one here, right? For each other parameter, you're going to have to put a comma afterwards, just like a regular object, right? Um, After that, mm, let's see, we get the data. So we say data is equals to rest.json. You need to trigger this JSON method. And this comes together with requests. After this has given you a response, that response object has a JSON method with it. Okay. And then that JSON object will now be converted into a Python object and it can be accessed using Python methods. So that means if you say something like data dot get, right? Remember here, where is it stored? It's stored under the code's key. So we need to access the code's key. All right. Um, so here you say codes because it's under there, everything that we need. Um, right. If codes doesn't exist, if I say not codes, so that means if is returning nothing, or if this is empty, NA, or does not exist, then I will break the loop. This is where I will break the loop. If not, then for Q and codes, or for each code in the codes, um, I'm gonna save the code, but I'm gonna have to create another variable here. So I'm gonna say all codes is a list. All right. And then I'm gonna say all codes. I'm gonna put all the codes here, append. Uh, sorry. All right. I'm gonna put here what's in there again. We have text. We have author, and then we have tags. So for the text, we can just get the text immediately. For the author, we can go one level further and then get the name. Okay, go to author, then go to name. For the tags, we can just these are all this is just a list, so we can just join them together. Yeah, we can just join them together, string them together into one object. So we can say something like text. So we are accessing Q, right? So you say Q dot get uh, text. So you should be able to get the text and the value of text, right? Yes, you can get that. Next is author, which is we need an additional step. So q dot get. You need to go to author first. Mm, so what is inside author? We'll use a blank for this one. A blank. And then dot get name. Okay, so we're going down further, author and then name. So you kind of need the blank part here for this to work. And then tags, you need to what? If we're gonna use the join method, then we have to indicate a separator. So that's a comma dot join q dot get. And then it's called tags. This is a list. So put them all in a list and then join everything together. Yeah. And after that, all we have to do is increase the page number. So you can say page plus equals to 1. And then it should go back and do the entire thing all over again until it reaches the point where the codes are nowhere to be found. Um, the code's key is nowhere to be found. That means it has returned an error. That means we have reached the end of all the contents that the site is able to give us. So that means when it's done, all we have to do is access all codes. We can pass it to pandas data frame. All codes. After that, you can print the data frame. Yeah, let's try this. API codes. We got this one. All right, so it's still loading. Uh, Okay, that's a lot of errors. Hmm. Where did it start? Uh, Get get ADDR info. This very copy. API codes. API for okay. It seems to be occurring at line 12. The response is equal to request. Request. about get. Why is it not highlighting? Response. Let's- Something's wrong here. I'm not really sure, but ah, okay. I think I'm missing one slash word. All right, that's not the one. JSON code error response dot JSON expecting value, but there's no value. Needs to be at the top first. Get codes. If not codes, then codes does not exist. Another exception occurred. Let's print the page number so that we can at least see what page we are. We can't even see the page number, right? Hmm. This is the top. Input rest that JSON. What is wrong with this part? Data. Okay. Data. What's that? 21. Mm, okay, hold on, guys. I'm sure we're gonna figure this out before the time. Yeah. Data 79, paste data, not define. I have it here. Try accept stop working. Geez. V bar start. I'm sure it's not params should add another one, right? Let's try this one. Oh, there we go. Okay. Two, three, four, five, six, seven, eight. All right. So print data frame. Why am I printing page here? And then I'm printing data frame. All right. Okay, this is another column. So three columns, text, author, and tags, and then these are the row numbers, and these are the content. So yeah, like earlier, it says Albert Einstein, the world as we have created it, and all the tags that are associated with it. All right. So now we essentially scraped all the all the codes on the website. All right. So the thing that I made a mistake earlier here because when you're using params, it automatically adds a slash in the end. But earlier, since I had an existing slash, um it became a double slash, right? There are two slashes there, so that became an error request. So you saw earlier that the error came here, right? So it doesn't always mean that the error is in that specific line. You're gonna have to analyze your code a bit and see where the error really came from. So I was really guessing that uh, it's somewhere before this one because I know that JSON method really exists. I'm sure of that, and I'm sure that if I use the get and API parameters, I will get a response with a JSON method available at that point. But I was not sure if it was requesting properly. Right, so this was the mistake. First, I was missing the first slash, and then second is I added an extra slash in the end. So you're gonna have to be careful with that. Okay. And with that, it's now 5. So yeah, we'll have to end here our session. Um, so not next week since it's the break. So I guess next year will be for your last session. Am I correct? With wow. 11 session. Yep, yeah, there's still one more. This is 10 out of 11. But this will be the last time that you guys will see me for this course, all right? And yeah, anything else you guys need before we end? All right. So there doesn't seem to be any question. And yeah, that's it. I'll upload the recording as soon as I can. And I hope you guys have a great weekend. I'll see you around, guys. Thank you so much for listening. Goodbye.